This video is about the celestial sphere, the sky we can see around us without using binoculars or a telescope.
In the lecture outline, the first four vocabulary terms are important reference markers on the celestial sphere. The next six are about the motions of the sun, and the last seven are about the coordinate systems on the Earth and on the sky. The sky around us can be imagined to be like a great hollow sphere surrounding the Earth, called the celestial sphere. You can see one half of the celestial sphere at any one time because the Earth, the ground you're standing on, blocks the rest of the celestial sphere. What part of the celestial sphere you can see depends on the time of day and your latitude, which is the number of degrees you are from the equator. Let's look at the important reference markers on the celestial sphere. If you project the Earth's north and south geographic poles outward onto the celestial sphere, you get the north and south celestial poles. The Earth's rotation axis intercepts the celestial sphere at the celestial poles. All the stars appear to spin around the celestial poles throughout the night, and the sun appears to do so throughout the day. Of course, we now know that the Earth is actually spinning underneath the fixed stars and sun, but the celestial sphere model is a convenient model to use to predict the positions and motions of the sun, moon, planets, and stars on the sky relative to your location on the Earth. If you project the Earth's equator onto the celestial sphere, you get the celestial equator. It is probably the most important reference marker on the sky, so you need to know where it is and how it depends on your latitude. Any object's daily motion, whether it is the sun, moon, planets, or stars, is parallel to the celestial equator. In just a little bit, we'll see how the celestial equator arc changes with your latitude, and therefore how all the object's motions arcs will change as well. The celestial equator intercepts the horizon at the points directly east and west anywhere on the Earth. We see just one half of the entire celestial equator circle around us because the ground we stand on blocks our view of the rest. Because an entire day, an entire 360-degree spin of the Earth, is 24 hours long, that means that any object on the celestial equator is above the horizon for 12 hours. Both the celestial poles and celestial equator are fixed markers on the celestial sphere, but the other two reference markers, the zenith and meridian, depend on your observation location. The zenith is the point on the celestial sphere that is always straight overhead. It is always 90 degrees above the horizon, and you can't get any higher than the zenith. The meridian is the great circle around the sky that goes through the celestial poles, the north and south points on the horizon, and the zenith. All objects' daily or nightly arc across the sky reaches its highest point when it crosses the meridian. When the sun is east of the meridian in the morning, it is ante meridiem, or AM, and it is rising up toward the meridian. When the sun is west of the meridian in the afternoon, it is post meridiem, or PM, and it is descending down from the meridian. Now we're going to take a look at how the sky moves from various locations on the Earth. First, let's look at a drawing that summarizes the motions all on one page. This picture is in your student guide opposite the lecture outline page. The drawing shows how your latitude, which is the number of degrees you are from the equator, how your latitude determines what part of the celestial sphere you can see and the angle the stars will move with respect to the horizon. In this picture and in the next ones that follow, each observer is observing the same star or set of stars. Next slide. In this set of pictures, there's a view from far away from the Earth to show the entire celestial sphere, with the north celestial pole directly above the north geographic pole, and the celestial equator projected outward from the Earth's equator. It shows the person's location on the Earth. Of course, the person is actually much, much smaller than the Earth, so from the person's viewpoint, the Earth's radius of curvature is much too great to see, and the ground appears flat. The person can see just one half of the celestial sphere at a time. That's the lower left picture. Looking out onto the sky in the south direction is the lower right picture. If the person is at the North Pole, then the North Celestial Pole is straight overhead at the zenith, and the celestial equator is right along the horizon. That means all of the stars, and the sun, moon, and planets too, will move parallel to the horizon as the Earth spins. You see the star circle paths in the lower left picture and the star paths in the lower right picture are all parallel to the horizon because the celestial equator is on the horizon. Next slide. As the person moves southward toward the equator, the North Celestial Pole is going to move away from the zenith point, and the celestial equator is going to pivot upward from the east-west points on the horizon. This set of pictures is for a far north position of Fairbanks, Alaska. Before we move on to the other locations, in your student guide where it says height of celestial pole above horizon, write the number of degrees the celestial pole is above the horizon, that is the altitude of the celestial pole, is equal to the latitude of the observer. For observers in the northern hemisphere, stars closer to the north celestial pole are above the horizon for a longer time than those farther from the celestial pole. The lower right picture shows this very well. The observer is looking south, facing away from the north celestial pole. The stars north of the celestial equator have big, high paths, while the star south of the celestial equator has a small, low path. In the lower left picture, the green star path shows that a large fraction of its total 24-hour circle path is above the horizon, so the star is above the horizon for more than 12 hours. Stars closer to the north celestial pole are above the horizon for a longer time. The red star path is for a star is close enough to the north celestial pole for it to be called circumpolar, meaning that we can see its entire 24-hour path around the north celestial pole above the horizon. The star will not set. Because the observer in Fairbanks is at a latitude of 65 degrees, all stars within 65 degrees of the north celestial pole will be circumpolar stars. By the way, at the June solstice, the sun's path is going to be just slightly above the green star's path, so in Fairbanks, the sun on June 21 is going to be above the horizon for over 22 hours. However, 6 months later, the sun in Fairbanks will be above the horizon for less than 2 hours. Next slide. This is the view from Seattle at a latitude of 47 degrees. It is actually the view for any observer at a latitude of 47 degrees, but I went to graduate school in Seattle, so I chose Seattle as the person's location. The North Celestial Pole's altitude equals 47 degrees, and the top of the celestial equator's arc reaches 90 minus 47 equals 43 degrees altitude, where it crosses the meridian in the south. The star paths are parallel to this more tipped-up celestial equator, so they make a steeper angle with respect to the horizon, and fewer stars are circumpolar. Stars closer to the north celestial pole are above the horizon for a longer time. Next slide. Now we're in Southern California at a latitude of 34 degrees. The north celestial pole's altitude equals 34 degrees, and the top of the celestial equator's arc reaches 90 minus 34 equals 56 degrees altitude, where it crosses the meridian in the south. The star paths make even steeper angles with respect to the horizon, and even fewer stars are circumpolar than in Seattle. Stars closer to the north celestial pole are above the horizon for a longer time. Recall that the sun on June 21 is going to follow a path just slightly above the green star path. The June 21 sun will get up high when it crosses the meridian, but not quite to the zenith. Again, note that all objects move parallel to the celestial equator throughout a day or night. Next slide. Now we're at the equator with a latitude of 0 degrees. The north and south celestial poles are on the horizon, and the celestial equator arc goes through the zenith point. The stars rise straight up from the horizon and set straight down because that's what the celestial equator arc does. Only at the equator do they make perpendicular paths with respect to the horizon. At all other latitudes, they rise at an angle with respect to the horizon. There are no circumpolar stars as seen from the equator. The equator is a special place. In all of the locations, you see that the celestial equator always goes through the exact east and exact west points on the horizon, and the altitude of the north celestial pole equals the observer's latitude. Next slide. This lecture slide shows several star trails pictures where the shutter of the camera was left open for several hours, so you can see the star paths traced out over this long exposure. The first picture shows the stars appearing to spin around the celestial pole. Looking in the opposite direction, you see the star trail arcs getting up highest as they cross the meridian. Looking east, these star trails show that the stars rise at an angle with respect to the horizon. At the top of the lecture slide is a link to a hands-on animation I created called Making Star Trails with Orion. And at the bottom of the lecture slide is another hands-on animation I created called How Star Paths Angles Depend on Your Latitude on the Earth. Unfortunately, they do require Adobe Flash, and I don't know how to code HTML5, so I'll show you in this video lecture what they do. You can then use this video scrub bar to go back and forth with it if you want. The Orion Trails one is a simple one to show how the star trails are made as you go to longer exposures, keeping the shutter open longer. The outline button traces the outline of the Orion constellation with 3 belt stars in the middle. The Make Trails button shows the trails after a 30-minute exposure and then after a 150-minute exposure. These trails are what you see with the star path angles animation. With the star paths angles animation, you can see how the angle the star paths make with respect to the horizon, how that changes with your latitude. It starts out at 0 degrees latitude with the observer, the yellow icon on the Earth globe in the upper right corner, on the equator. As you move north, the star paths tip over. Bakersfield is at a latitude of 35 degrees. When you get to the North Pole, the latitude equals 90 degrees, and the star paths are parallel to the horizon. As you go back to the equator, the star paths tip up to steeper and steeper angles.